Hello everyone, this is Module 7, Part 2 of Chapter 7, Database Construction and Application Processing. Where we left off in Part 1 is we were going through this database design, or we created this database design for the View Ridge Gallery database. We've determined what our relationships are, our primary key values, and all that in our database design. And I think we created the first two tables as we hear with we've generated an SQL script to create the structure of the first two tables. And what we started with here was artist and work. Okay, so we went through artist and work. Remember, we talked about the create table statement where we name the table as we have in the first example, artist, and in between the parentheses is where we add our column and data type information properties, as well as any of our constraint values, including designating our primary keys, alternate keys, and foreign keys. And then in our second example there, where we have the create table work table, in that particular statement, we're also expressing what our foreign key constraints are, as well as how we're going to force our minimum cardinality based on those two tables between artist and work, being a mandatory to optional minimum cardinality scenario. So just as a quick refresher, as we look at the create table statement in our first column, artist ID is indicated with an integer data type. So the first area, you name the column. The second area that you use is 3 columns. The second column would be your data type area. And then your third column would be where you would indicate your null, not null values, and then any other appropriate column properties that you want to indicate for that. So in this case, our artist ID column is indicated as identity. Identity is indicating that that's going to be a surrogate key value that's provided by the database management system. And in parentheses, the first one would indicate the starting value of that surrogate key, and then the number after the comma would indicate the increment value of that surrogate key. The next 3 or 4 columns should be self-explanatory in regards to the type of data type. So we have string values for the next 3 with 25, 25, and 30 in regards to character limitations on those particular columns, along with their null, not null status. And then in our date of birth and date deceased columns, we're selecting a numeric data type with some additional constraints where the 4,0 means what you're specifying, what's going to be before and after the decimal point for that numeric value. So we're saying is that we have four numbers that can be placed before the decimal point, and then there's 0 numbers after for both of those numeric data types. And then in our constraint, we're indicating our constraint in this statement, where we're indicating what our primary key is. So we indicate it as a constraint. We name what the constraint is, just in case we want to call back that constraint in a query or something else. And then in our first one, which is artist PK, which indicates what our primary key value is for this particular table. And in parentheses, we've indicated that our artist ID is going to function as our primary key value. And again, artist ID is going to be a surrogate key as well. And then our second constraint in this particular table, we've named that as artist AK1, which will indicate what the alternate key column would be in this table with the unique keyword. And we've indicated that that alternate key is going to be a combination of last name and first name values in this table. So that's just a quick refresher of what you see there. The second example, we have 2 different things that we talked about earlier, but just a refresher. The description column in the table work represents a default value that we would be giving. So if in the description, if there's nothing put in there, instead of a null value, the default value would be unknown provenance. And then we add an additional foreign key constraint down at the bottom. You see the last constraint in that particular statement. We named it as artist FK, which we've indicated the artist ID, which is in parentheses, as our foreign key that references artist ID in the artist table, which would be the parent table up in our top example. And then how we going to enforce minimum cardinality is indicated in the last two statements, where on any update there's no action, and on any delete there's no required action on the work table. Okay, so those are two quick refreshers in regards to what you see here. And again, what we're doing is creating our first two tables in this ViewRidge gallery database based off of what our logical design was. So again, what we came from a ER model. We transformed that ER model into a logical database design. Now, that logical database design comes, we actually put together an SQL statement that we can implement this into our database. So the next step we want to make sure that we understand is how we implement cardinalities. This is kind of a good table that you can reference on what you need to do for the different scenarios. So if we have a one-to-many relationship where the parent is optional, or a one-to-many relationship where the parent is required, what table constraints need to be put in place, what needs to be done. So for the first example, we know if it's a one-to-many relationship where the parent is optional, we need to specify the foreign key constraint and then to set the foreign key as null. Where in contrast, if we have a one-to-one relationship where the parent is optional, we need to specify a foreign key constraint and then specify the foreign key unique constraint, and then set the foreign key to null. So this kind of gives you a basic breakdown of what you need to do for each type of cardinality situation that you need to do in as far as implementation. So back to the ViewRidge gallery database, we've come up with some some default values on our tables that will be in the database. We see three different tables here that have some type of default value or data constraints that we need to implement on the data that will be input into the tables. So for the work table, we've already discussed that we do have one default value as unknown provenance. In the artist table, we have three different constraints that we're going to put on in regards to nationality, and then we're going to be, as far as date of birth, in the artist table, we have, in date of birth and date of deceased, we have some specific orders of digits that we want to be able to select. So when people put in a appropriate date of birth, it will coincide with the appropriate date of deceased, and so on and so forth. And in the transaction area, we're going to accept a specific value that's equal or greater to amount for sales price, and it's the same thing. We have date limitations in our transaction table as well. So let's take a closer look at what our SQL statement would be to implement these constraints. So again, we're looking at the artist and work table. So in that artist and work table, we have constraints on nationality, as we discussed, and then the default value for work that we've already discussed as well. So so if we look at our top example in the artist table, let's take a look at those additional constraint values that we put in here. So the first one that we're looking at here, let's take a look at the nationality values. So essentially what we're adding is what's called a check constraint. So with this check constraint, now we pass a data manipulation type statement that you should already be familiar with, because we're using the in keyword that we've discussed in previous chapters, with specifically chapters 2 and 3. So in our nationality values, we're going to check to make sure that nationality, the column nationality, and we say in, has to match one of these values. Okay, so it's going to check to make sure that one of these 8 values can be accepted. So what we can't do is we can't come in here and put something like Chinese or something like that. It will not accept it it'll end up throwing us an error back. So this is how we can control those values that we accept. Okay. The second constraint is also a check constraint, and this is where we're going to check the values, our birth values check. So again, in here in our second column is where we name the constraint. So if we ever need to call on this constraint and check it or look at it or change it, we can just call on nationality values, or we can call on the birth values check. Those are specific constraints that we've named. So for this one, we're going to check to make sure that the date of birth is less than the date of deceased. Okay? And then we have an additional constraint that we're going to put on our birth year and death year by making sure that date of birth, again, a check constraint here, where date of birth is for the, and what we have in here in single quotes is what we're going to accept for each one of the number positions of the date. So in the first position, it has to be 1 or 2. In the second position, it can be 0 through 9. Third position, 0 through 9. Last position, 0 through 9. So we should be able to take any values from, from the 19 whatever, 1800s whatever, all the way up to 2000 whatever dates in terms of date of birth to today's date. The valid death year would be the same way as here, but we just, and again, this check constraint would make sure that this value of birth year is always going to be less than the value of your death year, to make sure that we have a valid, birth year and death year, or, good integrity of information that we have in that particular table. Okay? So here's an example of how we're going to, again, enforce those default values and the additional constraints that we put on that table. Here's an example of a third table here. This is our customer table. And there's a slight error shown here in the customer table where email address is in the wrong location and encrypted password is omitted. So we have here, so this version is correct, but in your book it may show it as wrong. But make sure that you take a look and show, so if you don't get confused if you're looking in the book and what I see here. But there's, I think in the book this may be wrong. But notice here too, also too, is that we've indicated as, I remember we talked about this before, as email as an alternate key, indicated by our unique keyword here. But also too, it's allowed to be null. So we need to take a look at that as well. Remember, any of our key values, we want to make sure that we don't have any null value for that. Okay. Here's the rest of the SQL configuration structural statements, DDL language to create the rest of the tables in our database based off of what our constraints are. There shouldn't be anything new in this particular table. You can see here we have some additional check constraints where we're validating, making sure that the sales price is greater than 0 and the sales price is less than or equal to 500,000. Okay, and then the transaction date, we just to make sure that the date acquired is less than or equal to the date sold. So we're validating the transaction date, and then we're validating our sales price with these two check constraints in that particular table. Everything else should be self-explanatory in regards to what you see. In our intersection table here, this is fairly new. Where in our intersection table, this is given not only we're adding what our primary key is in this intersection table, which is a combination of artist ID and customer ID, but we're also indicating that those values with this check constraint are foreign key values. And then also too, we're adding some referential integrity statements here to make sure that we understand that the artist ID, part of the primary key, will reference the artist ID and its parent table artist. And then here is where we would indicate how we're going to enforce our minimum cardinality. So on any updates, there's no action needed, but if we delete anything, we would cascade those deletes to the parent, as well as our customer foreign key value or customer ID we'll reference the customer ID and customer in this intersection table with the same thing, is that there's no action on any updates, but if we delete anything, we would cascade those updates to its parent table. Okay, so these are the final two tables of our um, um, table design or table structure that we will be passing with our SQL statements. This is an example of how you can use SQL Server Management Studio to create a database diagram. In this class for assignment 6, we used Microsoft Visio to create our database diagrams. SQL Server is very easy to use to create data diagrams as well, to help you understand what your relationships are and all of that. Is because what you're seeing here, and again, it doesn't specifically use crow's feet notation, but what it's saying here is that in our obviously these are our tables or entities, what has a relationship with what. This indicates one to many with a mandatory, an optional type relationship. Our values, our key values are indicated here. But the way that you can create this database diagramming using SQL Server Management Studio is in SQL Server Management Studio, if you go to your tables that you've already created in there and you hit the plus sign, the very first entry should be database diagram. And if you right click on that and go to new diagram, it'll indicate which tables you want to use. It might give you a little message saying that all of the objects may not be installed, but you can just go ahead and click yes, and then after that it'll give you a list of all your tables that you want to include in the diagram, and then you can click on which table you want to include on the diagram and just click close, and then boom, it creates this database diagram for you to use to help you kind of figure out how you have your table, how you have your relationship set up, and which tables have relationships with what. So this is just a good, easy way to use SQL Server Management Studio to help you accomplish that task. So there may be some times where you may need to change some things after you've created your structure. After you've created your structure and you want to use, you say you wanted to change or add an additional constraint, you would use what's called the alter table statement. Okay, this can change any of the table structure properties or constraints after they've been created. So our first example is, say we wanted to add a foreign key value on our assignment table. We would just simply use the alter table assignment statement and then add and use the add constraint, name the constraint, and then notice here this should be consistent with what we've already seen in our SQL statements thus far, as far as how we built our tables so far. So the alter table assignment statement will allow us to add this new foreign key constraint, as well as what referential integrity we want to put on it, and what minimum cardinality enforcement we would add as well. The alter table statements we would use if we want to use, if we wanted to add or drop columns. Notice here that the column keyword is not used. In our first example, if we just wanted to add a column, we would simply just do a alter table customer, alter table, choose the table that we want to alter, and then we would add, and then just choose the add, and then name your column, give it a data type, and indicate what null value it is. Okay. As far as dropping an existing column, if you wanted to drop a column, it's just simply you again use the alter table, indicate what the table is you're using, and then use the drop column statement along with whatever column it is that you want to drop within that particular table. The alter table statement can also be used to add or drop any of the SQL constraints. You can also use it to create primary keys and alternate keys, set null statuses. You can create referential integrity constraints or create additional data constraints, as we did before. Let's see here. So in our first example, we're using the alter table statement to add a specific constraint related to a new check constraint to make sure that Robert's no pay is not in the last name column. Okay. And our second example there, if we wanted to just drop the constraint again, it'd just be the alter table. We indicate what the table is, and then just use the drop constraint statement and indicate what constraint based off of what we name that constraint. Again, remember how I told you we can call on those specific constraints as we create them. Removing tables, the drop table statement. The drop table statement is very powerful. It simply is, drop table transaction. It's going to drop everything in that particular table, and that table is going to be gone. The only caveat is that if there is any constraints on that table, you need to drop those constraints first. So that's what you see in our before. Otherwise, it'll give you an error. That's what you see in our second example there, where we use an alter table statement, where then you alter table and then drop the constraints that's in that table, and then you alter the table transaction and you drop the constraints associated with that, and then we can go back and drop the transaction table after that. But you would have to drop the constraints prior to that if there's any that exist. Same thing here. So this is just a breakdown. So essentially, if you wanted to drop that table transaction, you would have to, then we can go back and drop table artist, the intersection table. We can drop the transaction table or the customer table. But again, all of those constraints have to be removed first. Okay. The SQL truncate table statements. This is used if we want to just delete data from our tables. We want to keep our table structure, however, but we want to just delete all of the data that's in that table. We need to make sure that the only thing that, if we wanted to delete data, the only thing that we cannot do it is that if there's any referential integrity constraints on foreign keys that's being enforced, it will not work. It'll throw us back an error. So we need to make sure that we remove any foreign key constraints that's associated with those tables if we wanted to use the the truncate table command to remove that data. Also, too, bear in mind that this does not reset surrogate key values. So if you remove the data that's in the table and then we go back and add some table, more than likely it'll pick up where it left off, as opposed to reset and start back over at that initial value, which made whatever you indicated, like in our example before, where our index value maybe start at 1 or start at 500, it's going to pick up where we left off. There's also a create index command. This is used to help improve database performance. This is a special data structure that's created to improve data performance, but it also creates an index on all primary key and foreign key values. This way, developers can direct SQL Server to create an index on other columns as well that are used frequently in where columns or on columns that are used for sorting data when sequentially processing a table for queries or reports. So the index statement is not really covered much in Chapter 7, so it doesn't get deep down into it, but just understand that you have a create index, alter index, and drop index statement, just as well as just like the statements that we've already talked about with the basic SQL structure. Next up is more data manipulation language. This we should already pretty much understand because we talked about this in Chapter 3, I do believe, in Chapter 4 in regards to normalization. The SQL insert statement is in our first example here. We have an insert into artist. What we've indicated is in the first parentheses is our column values in the order that we want to receive those values. So, and then we use the keyword values to indicate which values are going to be stored where. So in our first example, you have Myro that will go in the last name column, Joan in the first name column, Spanish and nationality, and then 1893 in date of birth and 1983 in date deceased. It has to be in that order. Once you indicate your column order in that first set of parentheses, your values statement must match. Those values must match not only what those columns are, but the data types. So the information has to match the data types that's associated with those columns. Okay? Um, and in our second example, notice we don't have, well, let me see if this is an example here. Yeah, in this example here, which is considered a bulk insert, we don't have a values column. So this is what we would do, like if we wanted to do, if we're copying data from another table or another database into our new database. This is something that we, again, already covered in chapter 2 and 3. If we wanted to, again, normalize or denormalize something. Some of you have already faced this because I know I've gotten this question before. A lot of times when you start adding rows or deleting rows or changing things around, you get some non-sequential surrogate key values. This is not uncommon. You can't just use an SQL insert statement by itself to help avoid some of these inconsistencies. You need to refer to some of the later chapters. Again, like in our chapter 10, it'll kind of give you a little bit more of what you need to use in regards to keywords if you want to make sure that those values stay sequential. For the most part, in all of our assignments in labs, surrogate key increments really doesn't matter much as long as they match up with what you have in your intersection table. So really that's all you're checking for. But there are ways, depending on the database management system that you're using, there are ways to go back and change those surrogate key values so they are sequential, or you can get the right order that you want or whatever. But it requires a little bit more detailed processing of what you're doing, again, depending on which management system that you're using. The update statement. The update statement is used when we want to change values on certain values in columns. So in our first example here, we want to update on the customer table. We want to make sure that we set where city to New York City, where customer ID is 1000. So the set statement will be based off of whatever you have in there, whatever you want to change on your update statement. And then the where is the where clause or the condition that we will want that requires that change. Okay. You can do bulk updates as well, especially the bulk updates. Not much. I mean, it's the same format in terms of an SQL statement. And if we wanted to do something, just like in a bulk insert, if we wanted to do something from, make changes from another table, again, you see what we're doing here is just applying DML language and using a subquery where that subquery will pass us a value for tax rate where we will change where the purchase order number, purchase order dot number is equal to 1000. Okay, so this is a good example of how data manipulation language and data definition language is used in conjunction with each other. Okay. Next and last is another data manipulation type language, the merge statement. The merge statement is, first of all, it's not available in Microsoft Access 2013 and later. It was introduced in SQL Server 2003, but it's one of the newest additions, but essentially combines the insert and update statements into one statement that it can either insert or update data depending on whether some condition is met. So in this particular example here, it's when these two, so in our first example where you're merging into artists as a using the artist underscore data underscore research table as an ADR. So we're abbreviating ADR. So what we're doing is we're using aliases here where we're matching up. So if if the artist last name in the artist table matches up with last name in the artist underscore data research, and the first name matches up, then it's matched. If it's matched, then we're going to update our specific nationalities, date of birth, and date of deceased. If it's not matched, then we're going to insert some specific information here. So essentially, again, this is combining the SQL insert and SQL statements into one statement, so we can process something depending on if that condition is met. Okay. The SQL delete, the DML delete statement. If you can also use delete if you don't want to completely drop a table, but you want to delete certain tables, certain information from your columns. You can use the delete statement. What you have to be careful is that if you omit a where clause or a condition, you'll delete every row in the table. Okay, and that can be problems. So we need to make sure that you be careful with the delete statement. Also, too, again, if you use the delete statement and you go back and add rows to that table, your surrogate key values will not be reset as well. Your surrogate key values will again start where you left off, more than likely. The use of aliases, we've already talked about this. The use of aliases can differ depending on the database management system product that you're using. But they are useful, especially if you have long table names or whatever. This just gives a good way to more syntactically give you a little bit more room, because if you have something like a customer, in our example here, you have a customer underscore artist underscore int, which is our intersection table. You may just want to abbreviate that as CI. That way it makes a little bit more sense, especially in regards to our implicit dot notation that we use on our column and table relationships. So here, to me, like I said, depending on if you're explicit or implicit type, whatever makes more sense to you. The next set of slides is just the data for the VRG database, which you can put in for your examples. This can help you, again, work through some of the examples that we're doing here in the slides for your purposes, if you want to play around with some of the the commands that we just talked about. But this is the end of part 2.